welcome guys. So, in the last class we have been discussing the Monte Carlo simulations of polymer chains and we discussed the basic algorithm, and then we discussed some practical tips of how to perform a Monte Carlo simulation, mainly in context of the polymer chains. So, today I will take it further, talk about some more practical tips, and then I will briefly introduce some other computational methods apart from Monte Carlo that are used in polymer science. Okay, so let us get started. Just to do a brief recap, the basic idea of the Monte Carlo simulation is the following. You start with a simulation box. We always has been drawing the cubic box. It need not be the case, but cubic is the most common case, and in that box you will place your particles. It can be your polymer chain like a bead spring model, for example, but just for a general sake I can say it is a collection of particles which are at different positions in the box, and let us say we refer to those positions as Ri, that refers to say R1, R2 to Rn, where n is the number of particles, and then a basic Monte Carlo step correspond to a trial move to a new position, and then for that trial move we compute the energy change delta U, and then we accept or reject the move with certain condition, and we derive the Metropolis algorithm. If we accept it, then we set our Ri equal to Ri prime, and we go back to making a trial again and continue until properties of interest converge. So, let us see like what do we mean when we say properties of interest. So, in reality what we are doing is, when I am doing these simulations, to begin with I start with a state that is very far from equilibrium, and then the hope is that if I continue doing it I will reach a state of thermodynamic equilibrium. Okay. So, we will have some equilibrium or equilibration phase, after which we will reach the equilibrium if the axis here is the number of Monte Carlo steps, and after we reach equilibrium then we get a particular positions of different particles in the system. Now, those positions are not the only possible positions at equilibrium. That is one thing we have to be very clear, because what do we mean by equilibrium? Equilibrium does not mean that the system is frozen. The particles still continue to move. The only thing that is true is the number of forward transitions are equal to number of backward transitions. So, if a particle is going this way, it has probability also to go back in the opposite way, such that the rates of both the forward and backward processes are constant. So, constant and equal. So, after we reach equilibrium, then we do something known as a production run where you can average over those many conformations which are at equilibrium. Okay. So, to begin with, let us say I start with the polymer chain. The polymer chain would be very far from equilibrium. That means it may have very higher energy. We first bring it down to lower energy, close to equilibrium, and then look around that particular value and see like what is the ensemble average of say the end to end distance or the gyration radius that I am interested in. Okay. So, in the case of a polymer chain, then the property of interest can be, for example, Rg. So, when I measure Rg for a particular Monte Carlo step, I am getting the Rg for a particular conformation. So, in the beginning I can be very far off from an actual value. So, in the equilibration phase I may get down to certain value, and then in production phase I will keep on fluctuating around that value, which is some sort of a average value that we can refer to as say Rg square, because you know for the ideal chain model Rg goes to 0. So, if I am doing like an ideal chain, I should be looking at Rg square, not Rg. But nonetheless, when we get to equilibrium, we always remember that it is not a frozen state. We will have fluctuations in the system, but when we take an ensemble average, we should get the value that we want at equilibrium. And the other thing is that whatever fluctuations we have around the average, it should not be biased on one side. There must be positive fluctuations and negative fluctuations. So, as a practice, we always discard this part of the run, that is equilibrium. It is very important, the equilibration part, but that part is not used to get thermodynamic average, because those conformations correspond to conformations which are far from equilibrium. We only care about the conformations after we reach equilibrium. Okay. Now, if I look at say Rg square, it may take a longer time to start fluctuating around an average. It would feel like the property is converging after a longer time than compared to say some other property like pressure or volume or something else. Okay. So, a true equilibrium is only achieved at very long times, but since we cannot go to like very long times in simulation, the way to track whether we are gotten there or not just depends on how long we run. And earlier it used to be that how long it run depended on how much the computer can do, but now the computers have gotten faster. So, now we can afford to do pretty long runs, at least for system sizes which are not very large, and we first do a run long enough and start to see whether the Rg value or whatever I am interested in start to fluctuate around an average, and then we start doing a production run. And the key is we take many samples during that production run, and then I take an average over those samples. Now, you may well ask that why I am taking a sample in the plot that are somewhat farther from each other, why not take samples adjacent to each other? Why do we discard these open circles that I am drawing, which are in between these closed circles? And the reason is, if I take the points very close along the trajectory, or if I take points just at the next step or the step after it, these points corresponds to states which are highly correlated, because within one step I am only moving one particle in the system, every other particle remain there, right. So, these samples which are like very close on this axis basically are highly correlated, and for the purpose of getting an unbiased average, we want to take average over uncorrelated samples. So, this is average over uncorrelated samples, there are ways to measure correlations, and we will discuss that later in the course. But the basic idea is that if I take samples at distant intervals, then beyond the interval that we have chosen, it must be such that the particle has lost the memory of the previous step. If I take a very close Monte Carlo steps, the memory will remain there. We want to take samples distant enough that the memory is lost, and we will come back to this point when we discuss the Brownian motion later in the course. Okay. So, this is the idea. So, we look at property of interest mean, property I am interested in, and I have to do long enough until that converges. For equilibrium, of course, we have to take infinite time, but since we cannot do infinite time, we live with the fact that we first do a run long enough that we can do on a computer and try to see whether the property of interest is converging around an average value or not. Okay. Now, there is some problems with this algorithm related to the computational time. So, if you think of this, at every step I am computing all the pair interactions between all the pairs of particles, and I am summing them over because I am interested in the energy change due to the move, and energy at any particular state is a function of all the pair potential energy. Actually, it is just sum of all of them, and since a move will result in change in the position of particles, we have to recompute all those pair interactions, at least those that are involving the particle that is moving. Okay. So, now if I start thinking in this term, then at every step we are doing of an order of n square computations of pair interactions, simply because there are n square pairs. Okay. So, now if I think in terms of computational cost, the computational cost will be of the order of n square, which means if I go from one particle to two particle, my code will be one quarter slower, or if I double the number of particles, my code will be slower by 1/4. Okay. So, the scaling up of systems to larger sizes will not really work. If I am starting thinking of say 1000 bead polymer, and if I go to 2000, I am actually going to a cost that is 4 times higher. Okay. So, there are some way to reduce this computational cost, and one of the most common ways is using a cutoff scheme, which basically works like this. If I go back to my picture of simulation box, I had like particles positioned everywhere, and each particle is interacting with every other particle. However, if you recall the definition of the pair interaction, I used a Lennard-Jones function that was something like this, and you can note here that in the Lennard-Jones function, if I go very high in the distances, the energy values are very small. In fact, if you go to say r equal to 2.5 sigma, that is one of the standard values where I will see like why it is important. At this value, the u of r is typically already less than the kBT, that is the thermal energy. And I have earlier told you that any energies which are like less than thermal energy are typically less important, and they can be ignored, because if the interaction energy is less than kBT, the entropy will dominate in that particular case. So, what this means is I need not look at all the pairs of particles in the system. We can only look at the particles which are within a cutoff distance, which can be set as, for example, 2.5 sigma, because beyond this cutoff, in any case the interactions are very small, right. So, for every particle I will draw a small volume RC. Only those particles which are within that volume will be considered for the interaction energy with that particular particle. Those which are like outside this volume will simply be ignored. Okay. So, keeping that in mind, now you can see that at every step I am not computing n square interaction, because for every every particle I am computing a much lesser number of pair interaction than compared to n square. So, what it means is my computational code will be much faster depending on the cutoff distance, subject to the fact that I will make a small error in the energy because I am cutting it off at some value. So, let us say if I cut it off there at 2.5 or whatever I choose, and let us say after this point my energy values are 0 and before this point it is positive. So, I will think of a revised graph that looks like this. Beyond RC I would think it is going to 0. That means U of R is equal to that given by the Lennard-Jones for R less than RC, and it is 0 for R greater than equal to RC. This is what is called a truncated interaction. Now, there is bit of a problem here, that if I look at R equal to RC, at that point the energy is discontinuous. So, this creates some problems because in certain algorithms we are interested in the gradient of the energy. I will talk about molecular dynamics in some time. So, in molecular dynamics I am interested in the gradient. Okay. So, in those cases, even otherwise, even in a Monte Carlo algorithm, this discontinuity is known to give you some artifacts, and it is better to have a continuous energy function. So, it is a better practice then to shift the potential such that I will make it 0 here, and I will make that small correction corresponding to the U value at cutoff. It will barely make any difference here, but it may make like somewhat larger differences towards the cutoff distance. But by and large, the advantage of this is I will not have any problem because of discontinuity of energy. So, in that case what we use is known as a shifted and truncated potential, which is given like the R value minus RC value for R less than RC, and it is 0 anywhere for R higher than equal to RC. So, now it is continuous, and now that problem is gone. Okay. So, this is like one of the ways I can make the code faster, because now I am looking at fewer pairs. It will only work for the short range interactions, or it will only be more efficient for short range interactions, for which at certain cutoff distance the energy become very small. If you think of, for example, a long range interaction like Coulomb, that decay is less rapid, and then we have to take either a very long cutoff or maybe think of something else, and there are advanced schemes that work in those cases. Apart from cutting it off like in this particular way, there are more smarter way of doing it, which I will not go into details, but if you want to read up, there are more efficient schemes known as wordlet list, cell list. Okay, so that is one of the main things that we have to keep in mind if I want to make my Monte Carlo code very efficient. So the next thing that is important in this kind of a simulation is like what boundary conditions do I employ, okay? And it turns out that the boundary conditions are sometimes very critical to the performance of the code, and exactly more importantly what system we are trying to simulate. So one of the boundary conditions can be, for example, that I will keep my particles in a closed box, okay. So let us see like what exactly are we modeling if I am confining say a polymer chain in a closed box. Let us say think of a carton, for example. So let us say that the sides of the box are closed like a carton, and we have a polymer chain that is present in the box. Now as you can see, now the polymer chain will keep on moving within the box, and many an occasion it will hit the walls of the box, and once it hits the wall with a box, it may have, for example, an elastic collision and come back, and then maybe it will reorient itself, and maybe after some time it will hit some other boundary, okay. So what this means is like it corresponds to a system where a polymer chain is indeed contained in a very small box. It does not capture an actual system that I was thinking to model, where I had a beaker which contained a dilute solution of polymer, for instance, and as I was saying, I will take a volume in the container that contains a polymer chain, because that imaginary volume that we draw in the beaker did not have like a real walls. It was not like there was some wall there for every polymer chain, it was going there, hitting it, come back. The walls of beaker are anyway not considered when we are looking at a small volume around the polymer chain. So in fact, if you look at this particular volume or any volume within the beaker, it will not be that only one single chain will be confined there. It can be that that polymer chain moves away and some other chain present in the system comes in that volume. So the polymer chain that I am seeing in a imaginary box inside the beaker is not the one which is confined. It is really dynamic. The polymer chain can come and go, that is one point. And if I put in or impose an artificial box, I will be introducing some artifacts because of the fact that now the polymer chain will collide with the box and come back and remount and do weird things, okay. So is there an alternative? And answer is yes. So if I want to represent a bulk system, an infinite bulk system, a better boundary condition is what is known as a periodic boundary condition. And what we do in this case is the following. So now I will think of my simulation box having replicas in 3 dimensions all over. That means if a polymer chain is contained in the box, what I will assume now is that this box repeats itself or has replicas in all the directions. I am only drawing in 2 dimensions here. And just like a polymer chain is contained in the box I am simulating, so this is my simulation box, and these guys are my periodic replicas. I only simulate what is happening in the simulation box, but then I assume that the same polymer chain at the same positions or relative positions are contained in all of those boxes. So, now the advantage of doing this is the following. Now, if any particle now hits the wall, there is no elastic collision. Now, if it is hitting a wall, actually it will simply keep on going as if there is no wall present. Okay. What we do then is the following. So, let us say now the polymer chain during simulation crosses the wall, then a bead comes on this end. All I do is I will forget about this bead and I will bring in another bead from that side, opposite side, which was the image of the guy that is lost. So, I will call all these polymer chains images of this chain. Every time a bead or a particle moves out of the box, one of its images comes from the opposite end, and in this way the wall effect is being modeled. The advantage now is, like, this entire polymer chain can then move out of the box and a chain containing its image can come into the box. So, there is actually no actual box being simulated, there is no wall effect at all. Actually, the whole idea of the wall is just imaginary. I can think of that my simulation box is not this entire volume. I can equivalently think of my simulation box as some other cubic volume. This is equivalently a simulation box, because again we will have the polymer chain and its replicas. Everywhere I place this simulation box in the volume, as long as the volume is being held fixed, I am actually modeling the same system. Okay. And this is the whole essence of periodic boundary condition, that, and this is the way it is helping you model an infinite system, and this is the one that is most commonly employed in all Monte Carlo simulations. So, with this I want to stop here. In the next class I will briefly discuss about what is known as molecular dynamics method, and then we will continue to talk about the thermodynamics of polymer solutions. Thank you.